Hello students, welcome to EduSil. In this video, we are going to discuss about load balancing. Basically, this topic is a part of cloud computing, you can say, or some other topics are also there which are related to our approximation algorithm. Basically, we are giving the solutions to all the problems. As we have already studied in the first video, I clearly mentioned what is algorithm. That time we discussed algorithm is a set of solution steps that we have to provide. So there might be different problems. So for different problems, the solutions are also like this. Okay. So load problem is one of them through which we can at least tell which of the machine might be in a network. As you have already know, within a network there might be different devices are being attached. Okay, so based on those devices which are actually processing, whose processing is high, whose processing is less, which one is fully loaded, means fully loaded in the sense like who is going to get all the requests from the clients, which is not exactly getting the request. In case of, you can say, load balancing is also a part of when we do the scalability of things. That time load balancing is also playing a vital role, as well as cloud computing, that we know when the computers are getting attached to a network. Whenever we are searching a file, or you can say running the algorithm within the system, whichever is nearby the node, that is a part of it. Also whichever is nearby the client, that will be solved. So in some cases also, which is an ideal condition, like some CPUs, or you can say some machines are available for giving you the results. Out of those, if one only is responsible for giving all the results, that will be a problem again, because if in case the machine is overloaded, or might be burst, or might be anything, okay, suppose cut out from the network, so that will be a problem then. That's why we are reading load balancing. In general, the best example I can say, in your might be those who are watching this video, you might be doing MTech, BTech, MSBS, or any kind of bachelor degree or MS degree, or might be, you can say, BCA, MCA. You belong to some course. Okay, from that, what exactly you have to do, like you have definitely form a group whenever you are having a project. So definitely, if you have 4 members in your group, if one is lightly loaded out of 4 members, definitely you are blaming like why you are not working. Why? Because you are overloaded. So if the load is properly balanced, means you have to submit a project, the project has to be properly being divided among yourself, as well as you have to do the work as per your division, like as you have already divided earlier. Based on that, you have to complete this much of work. So this will equal all the loads provided to all the students in your group. That will be definitely a proper solutions for giving the load or completion of project. So this problem might be happening in we have seen 90% of cases in a group. Definitely two or one member is exactly working hard. Why? Because he or she has to submit it properly. That's why they are working, and others are there who are just as a back support for them, not doing anything. For them, how we will properly being giving the work, or how the load will properly being balanced between all the group members, that is a part of our solution. Even if I'm taking with the group members towards the example which we discussed earlier, like in cloud computing case, how the task is getting circulated among all the machines, that is a part of our target here. So from the beginning, I must tell you, like the task whichever we are working, this is just a process for us. So each process we have to run for one time in a system. We should not focusing like that will be divided. So as you might be having idea about threads and processes, we are not segregating into threads. This is not exactly being in load balancing case. In our approximation algorithm, we have to take a job, and a single job will be processed on a machine. That is what we are doing. We are not dividing it. We are not dividing any jobs. We are simply taking the job and we are running in the system. Whichever is having load time, that we are providing. How it is getting exactly done, so I'll tell you this one. So basically this content I'm following, as I am already told in all the videos, like where I'm collecting the contents for this video. For making of this video, I'm collecting the content of core, you can say, the Trados book PPT where I've collected from Kingston, Princeton University, as this is already being existing there. I'll also keep this link where I've collected in the description of this video, that you can definitely get it. Okay. So for the load balancing, we have to know what are the uh, you know you can say the LITI, what are these exactly being called? Naming conventions we should know. M identical machines. Okay, there are M identical machines we should work. Next, how many number of jobs? N number of jobs. For job J, like definitely we should have like how much time it will be needing to complete one task or one job. So that is what called as processing time. It takes time to complete a task is called processing time. We are deciding it here as T of J for job J. Okay, there are n number of jobs, m identical machines, identical in the sense the same configuration are there in a machines. Okay, like if 4 GB RAM you're taking, so 4 GB RAM throughout all the machines. Like there are four machines with having 4 GB of RAM, so you have to allot 4 GB. There should not be any discrepancies over all the machines. Why? Because you cannot understand, like if I'm just giving the performances, so that time it will complete the job within the time. So that's why we said identical machines we should work. Next is job J must run contiguously on one machine. Okay, so that is what I told you earlier. So we are not going to segregate it. Once a job is getting assigned, we will give to one machine. Direct job will be provided to a machine. We are not segregating the jobs into different hubs, or we are not distributing that again. So job, one single job or a single whole job will be given to one machine. Okay. Next, a machine can process at most one job at a time. Means for the same time which is getting provided, at the same time the machine is allocating for the job, and the job has to complete. Once it is completed, then we will allow for other jobs to come. Okay, based on certain rules we will decide that one. Well, I'll definitely go through that one. That would be better to understand. Next, then what do you mean by load exactly? How to find out load? To find out load, a JFI, which is just a subset for a machine I. Okay, certain jobs are given, which is a subset of all the jobs. Definitely, we must say. So, machine I, the load of machine Li, which is represented as Li or L of I, you can say. Sigma, this represents sum of all jobs which are there in a subset with a processing time. The processing time is attached to each job. We will also clarify our doubt in the example section also. So I must tell you the load is the number of jobs for this machine we have to count. What exactly we are again counting in depth? We are counting all the processing time attached to the jobs. Clear? We are just adding all the processing time attached to those machines, which is named as I. Okay. Next, max span. What does it mean? Max span is the maximum load of any machines. Might be you just think there are four machines with different loads, whichever is maximum load. Suppose in your group, as I told you, I'm just repeating that one. Suppose a project, it took 2 hours to complete for you, or might be there are four members, one, two, three, four. Four members are there. I'm just saying in hours. Okay, for hours. One of it is taking 4 hours to complete. It is taking 3 hours to complete. It is taking 4 hours to complete. It is taking 5 hours to complete a project. Okay, so out of this we can say it is load among all the machines or all the persons. This is just a load, like 4 hours load that you have taken. 3 hours load is taken by the second person. Okay, this is just a person for us in a group. Okay, so whichever is greater, we can say it is a max span for us. It is max span. Okay, this is max span. We're just naming that one as max span. So this max span has to be minimized. That's why we are reading the load balancing. Assign the job to minimize max span. This is our target is like we should have to assign all the members here should have to work at least 4 hours. for identical, like if you can say like how to balance our load, if you just say balancing of load, I'm just writing it here. If I'm saying balancing of load, 4 hours each person, this is our optimal result. Like all should work at least 4 hours, but out of this fourth member who is might be you just think of, you are just working for 5 hours and all are working less than you, so definitely you have worked hard. So max span is 5 hours, okay, which is that you have done or contributed. If you can count all this divided by the number of persons, so average will be your load balancing. Okay, average if you're finding out, so this is what the optimal load balancing, which is named as L star. Whenever you are just taking average of it, this is our load balance. Okay, so that is what I did, like 4 plus 3, uh, 4 plus 3 plus 4 plus 5, and just dividing with the number of persons who are 4 here. So based on that we found the proper ideal exactly what we are going for. Okay, so it is 16 by 16, 16 by 4. So we should expect the load, which is optimal load. The expected load should be this much for all the persons. That's why we can say it is also optimal load for this example. Okay, this is just an example through which at least we should know what the theme is. Okay, so I hope you clear about the introductions with the basic example which I have taken. Next is load balance, why it is taking place. Before that, partition is there also, like we have to partition each of them, each of the problem. So load balance, we are just making it polynomial reducibility. Okay, when we are doing that one. So suppose there is job A, job B, C, D, E, F. These are just machines we are just assigning one by one. So using greedy approach, you just take a greedy approach, we will decide that how it is working. Suppose A is a first job. Out of, like, there are two machines in our example. A will be assigned to any of them. If you have assigned A, then for the greedy approach, what it says for the greedy approach, we will read that one on a list scheduling how it is working. Before that, the example we are just having with us. So A, we are having, like, here the initial load is 0, nothing has been given or nothing has been assigned. So A is assigned to one of them, either machine 1 as per the example they have taken. Next, next job will have to be assigned to machine 2. Why? Because it was previously loaded as 0, means nothing has been given to that machine. That's why we initially provided B. Next, what happened out of this, A and B, which initially that I'm just writing it here also to make you clear. A is taking this much of time and B is taking this much of time. When we see A is more than B, so for this lightly loaded is M2 now. Whenever we are having the third job to be assigned, so we are assigning here as C. Okay, why? Because it is lightly loaded. We are just following the greedy approach. Greedy approach. Just an approach, greedy approach we are following, which is named as least scheduling. We will be deciding, we will be knowing exactly how it is working in the just the next slide. We will decide. Next, C we are having, so here M1 and M2 lightly loaded is this one, means already completed with A, just before to that one, so D will be added again. So like this we are having added with the D. So whenever we added with the D, so both are in a same level. Okay, when we are having the same level, that's why we are just introducing we have two options. Then if both are having the same time, so whenever a new job is coming, like you can say job E, if it is coming, so it will be attaching with M1 or M2. It has two options then. So here they, as for the example, they just sorted with this second machine. So once the E started, next F is to be coming. So here M1 was free, then it attached there with F. So once F is completed, then G is coming again. So here F is this time and E was this time. So what exactly it has to do? So it will be adding with the machine which is having less load. So in this way we are just adding one by one load. Okay, so I hope you clearly understood. For that one, we are just considering the algorithm, how it is become working for you, which is named as a list scheduling, which is following greedy approach. Okay, which is following greedy approach. So for this, consider n number of jobs in some fixed order, like we are, you can say arbitrary order also, because we are not following any certain concepts here, like whether we are going to add it, might be or subtracting or might be sorting it. We are nothing to do. Like we are just simply saying we're just randomly we're picking the jobs, so that's why it is just written as some fixed order, but we don't know exactly how it will be like. Okay, so the job J, a machine whose load is smallest so far, we will just assign that job to the machine which is lessly loaded, or might be whose load is less among all the machines. As we have decided, like with the with the example, there are two machines. So based on these two machines, which one is less loaded, the new jobs will be assigned to that machine. If less, if load is less, load of any machine is less, then the new job will be assigned to the machine. Okay, so to the machine we will assign the job to the machine which is having less load. Will assign the new jobs. Basically this is what we have to do. Initially what is there, m is the number of machines, n is number of jobs. These are processing times. Okay, I'm just repeating it. Machines, this is jobs, this is processing time. Okay, so next for loop is started for all. Initially what we have to do, like we have to say all the loads will be 0, and the jobs which are the set of jobs for each machine will be assigned a 5, means nothing has been assigned. Clear? So this is what the initial condition. Initial condition. Whenever we set with the initial condition, then we have to go for the assignment. So assigning of job, assigning of job or assigning of new jobs. Okay, so like here we have to take j which is to be assigned. Okay, so here number of like we said the number of jobs are n, so we started with 1 to n. Next I, which is the machine which, like whenever we find out which machine is lessly loaded, this will tell us the smallest load. The smallest load, it will tell us which one is having the smallest load, we are picking that machine. Then what we have to do, like the j which is being selected, that will be added as a new job. Clear? New job in a subset. So that is what it is written as assigning of job. Once it is done, so we must say the timing when we said, like as I have already told you, the load will be summation of, load will be, as we have already studied, load will be summation of the number of jobs. You can start, it belongs to j of the capital J of I, which we have already studied, with the processing time. Like we are just adding all the set of jobs with the processing time. This is what a load of j. For the machine j, we have to find out this one, then only we can say or you can say, suppose load of I, sorry, I must write it L of I for each machine. Whenever we start with that one, so it should follow The JFI, which is basically the it follows certain rules and regulations, as we have already studied this one, like L of I, which is summation of all the set of jobs there within the machine I and with the processing time. We just recently studied that one. That is why I'm just saying you. So in this way we are assigning each job. Clear? In general, we can say the time complexity, because we are using two for loops. In general, anyone can say overly when he or she used to see, he or she can say n plus m will be the time complexity. But this is not. Why? Because you need to use the priority queue. As we have already studied in the heap time, how heap is getting created. That time also I created the video. Those who are new, kindly watch that one. So whenever we started with the finding of the load, that time it will be using the priority queue. That time it will be, instead of n plus m, it will provide you n log n, not from the iteration method. You don't find that one directly. Whenever you are trying to use the data structure, basically we are using queue, which is priority queue. Through priority queue, whenever we are using, the time complexity is taking is big of and log n. Okay, I hope it is clear to you, like how greedy approach, how basically how list scheduling is providing with this much of time. Okay, next we have to follow certain lemmas and we have to prove a theorem. Okay, so Graham's 1966 algorithm is a two approximation that we recently studied in approximation. Those who are new, kindly watch the introduction video. What is two approximation? What is one approximation? I'm just repeating with the preview of it. Like one approximation, whenever we are saying one approximation, it is equivalent to the optimal solution. Okay, so it is optimal solutions. So one approximation above than it, suppose 1.2 or 1.5 or anything, we are just saying that one as. So if it's two approximation, I'm just saying. So the two approximation is 1 plus epsilon approximation. This epsilon gets 1 because previously that we are having 1, like we have to at least get optimal solution. Another that what exactly we are getting is considered as epsilon. Okay, that epsilon value is 1, epsilon value is 2, 0, whatever that we are getting. So that is what we should say. The two approximation is equivalent to 2 times more than the optimal solution. Okay, so whenever we are finding the optimal solution, that is a kind of way we are following, which is approximation 1. Through approximately we are just getting it. So whenever we say two approximation, it is 2 times more than the optimal solution. Suppose optimal solution is, suppose you are trying to find out distance between two different squares at your location. Suppose think there are two different squares. Let us take this as example of like A to B. Suppose you are moving, there are also C to D. There are suppose there are only two ways to start with A to B. So you have found out like there are 3 kilometers. Here is 3 kilometer and 3 kilometer. So your approximation is saying this one, which is 6 kilometers. Your approximation algorithm is saying 3 kilometers, and the optimal is providing 3 kilometers. Optimal is giving 3 kilometers. So this is what we can say, it is two approximation. Okay, so because you are getting just 2 times more than the approximation, that's why we are saying it is two approximation. Just for an example I'm just giving. Why? Because other than that we must not tell this is a detailed video for us, because detailed video means we will know every details of it for one by one. Okay, so I hope you understood it. Now our theorem says like we should have to prove this. The greedy approach which we followed in list scheduling is giving us two approximation. First, worst case analysis of an approximation algorithm. Next, need to compare the result with the optimal max span. Basically we will do that. These are just lines it is written. So now a lemma means we say it is true for a purpose. We said it is true. Whenever we are using lemma as a you can say keyword, that time we said it is true for this condition, or it is true for that condition, with, or it is true for a whole. Like we say sun rises in the east, so in that case we could say it's lemma, but it is exactly a part of lemma, but it's a true, by the way. Okay, so whenever we say true table, that time we say we have also studied in the mathematics what is lemma. Okay, So a theorem that time we have studied it, but I'm just initially telling you like why we focus on lemma, because without lemma, without some initial conditions, we may not solve it further, as we have done in recursion also. In recursion, we initially as taken the values whenever we find out to the recursion, that time we are just keeping otherwise condition. Okay, because in a recurrence relation, whenever we followed some recursion concept, that's why we said like for a base condition it should follow certain solution steps. Okay, so this base condition is a lemma for us whenever we are using the recurrence relation. Again, I'm telling you, if you do not know, if you do not correlate with the lemma with the recurrence relation, kindly watch the recurrence video. This is there in a additional video. You just find it out and just read it, like why it is needed, why base condition is needed. So this base condition, when we studied that time, it's equivalent to the lemma here. Okay, now we will come back to our topic, list scheduling. Okay, so here L star, as I told you, L star is represented as the optimal max span, or you can say the maximum load for all the machines. That should be optimal, means it is for all. This is the correct one which we are expecting. Okay, so for this lemma, definitely we know whatever the jobs are, so maximum of all the jobs definitely is greater than equal to the optimal span. You can think like there are machine 1 and machine 2, we recently completed with that example. I'm just giving you like suppose there are two different jobs, there are four jobs we can say. Okay, with the processing time, I'm just writing processing time 1. I'm just writing it outside. One process here is processing time is 2. Here is 3. Processing time is 4. Okay, I'm just giving you just an example of it. So whenever we assigned, suppose I'm assigning 1 this side, next I'm assigning 2 this side. Why? Because the load will be properly, either you can say 1 will be assigned to M2. If you are assigning any of this, so definitely the next job will be the rest of the machines allowed allocated there. So here, as we know, as per the greedy approach, the less time is 1 M1. So we are adding the next job is 3 here in this side. Okay, this is just a processing time. I'm just writing on the above. This is just a processing time. Okay, so processing time. Now 4 will be added this side. So then if I'm asking what's the load here, load you can say 1 plus 3, it is 4. 4 is the load. Load 1 is 4. Load 2 is 6. Clear? So whenever we say as load 1 and load 2, as I told you, the optimal solution would be, we are not going to divide that one. As for the job, what we have to do, the optimal is like either you can give 1 plus 4. For this is our approach, for greedy approach we are having this one, greedy. So if you are having the optimal one, I'm just writing it here, M1, M2. So the optimal could be, here it is 1, here it is 4, here it is 2, here you have to provide 3, which is 5 and 5. We must tell the L star would be 5. Why? Because here the L1 is 5, L2 is 5 and L1 is 5. So for this max span, I must tell you the max span which is we are getting is 6. Okay, so L2 is a max span. I'm just writing it, max span. Max span is L2. Why? Because the maximum among all the loads provided, all the loads of, means loads assigned to all the machines, the maximum is 6. So this is what our max span is. So whenever we compare with this one, so we found the optimal result is 5. Whenever we say the lemma, for the lemma condition, we must say 5, which we got from this example. Okay, from this example I must tell you 5 is greater than equal to 4, yes or no. Means out of this processing time, the 4 is having the maximum one. So 4 is maximum, so I must tell you not equal to sign, I must tell you like it is greater than. So here is the maximum of 5 is greater than 4, which is this one is optimal, this one is maximum of all the processing time. Okay, max j t of j means all the processing time, maximum of all processing time, maximum among all the processing time. Okay, so I hope you clearly understood how we are getting it. Okay, next is, as we have decided like the processing time or whatever the processing time that we have, okay, we have to just take the average of it. Whenever we are just doing the average of it, whether it belongs to this or not, the same example we will be taking care of. Okay, so the average is 1 plus 2 is 3, 3 plus 3 is 6, then 4 is 10. So in this case what we have to we have to say 10 is the maximum, like we have to add it. It said like we have to add it for a single machine. What exactly we are doing? So for total processing, whenever we say, it is taking the total processing time. Next, 1 by m fraction we are taking for one machine. Suppose the ratio we are finding out. So the here I must tell you the this side is 5, and whenever we are taking the ratio of all the processing unit, so 1 plus 2 plus 3 plus 4 divided by the number of machines, because we are just taking the ratio of it. Whenever we are taking the ratio of it, so whether it is less than or not, that we are just taking an example of it. Okay, less than or equal to, we have a question mark. Next, 5 this side. So here when we add it, like it is 10 by 2, which is again we found 5 equal to 5. So this lemma verifies that. We verified lemma 1 and lemma 2 from the example. Okay, this side we must tell you this one, this m is number of machines that we are having, and this t of j is we are just adding. Clear? So we are adding 1 plus 2 plus 3 plus 4. This is what we have done, and we are just checking with the lemma whether we are have successfully proving this one or not. So I hope it is clearly understood, like the lemma, how we are getting it. Now we will focus like how to say the greedy algorithm is two approximation algorithm. Okay, so let us take like whenever we assign the maximum job to the machine which is lessly loaded or lightly loaded, basically we must say it's lightly loaded compared to all the machines. So we can say it is L minus, before adding the T of J, we must say it is up to this, which is like L of K. L of K represents even all the machines from 1 to M. There are machines from 1 to M. Whenever we say this, we are considering for this, and this is an example which exactly less than the load assigned for all the machines. This much of time is definitely less than or equal to all the machines. So I'm just giving you just an example through which you can definitely understood. So as we have taken the examples there, I'm just saying you six jobs for three machines, three identical, or you can say three machines, and one job of three jobs having six jobs. I must write that one again because processing time I'm just left out with that one. Six jobs with are having processing time uh, one for three machines and one job having processing time 3 for again 3 machines. How do we allocate? How do we allocate that we will decide that. So there are 3 machines, M1, M2 and M3. Whenever we are adding for the first job, like out of 6 jobs we have to add it. So for the first job, like I'm just writing on the above, like what should be the processing time of it. So after there are other jobs are to be assigned, and there are two machines. So any of this could be selected. Then now we are completed with the 2 jobs. There are 4 jobs left. Next, though it is free now, we're just adding with 1. Next, once it is completed, like again we have the same conditions prior to that one. So we are going to add another job which is 1. Next, another job we are adding, again the same procedure I'm following. So next 6 jobs having 1 processing time we have added now. Okay, now one job is left out with where processing time is 3. Either you can add here, you can add here, you can add here, anywhere. Suppose I'm just adding 3 because we have same options. Now I'm adding it. So the processing time for this, or sorry, the load for the machine 1, which is L1, is 2, L2 is 5, and L3 is 2. Clear? So out of this, the max span, I must tell you, the max span is L2, which is 5. Clear? And I must tell you, like the optimal one, for the optimal, if we would allow the maximum one to be assigned first. Clear? We just think for a while. So here I'm just taking the maximum is this one, and I'm just allowing this, next for this, next for this. Okay, next. In this way we must tell the processors having different types of this. So it is L1 is 3, L2 is also 3, L3 is also 3. So in this way we can say the optimal max span, which is L star, is 3. Clear? So this is our optimal result, this is our approximate result. So out of this we have already studied in the previous video in the introduction of approximation algorithm, which is whenever we are finding the ratio of it. So 5 by 3, which is nearly equivalent to 6, or you can say it is 6 to the bar. Okay, so this is what exactly we are finding out of the result. So this is 1.6 approximation, you can say, or nearly equivalent to 2 approximation. Whenever I am just taking this example, so I must tell you it is a 2 approximation approach. 2 approximation. Okay, so we will decide that one now. With the same example, if you can take with any of this as J, like we are not adding it, so it is definitely equivalent to all the loads assigned to each machines there. Okay, this is what we initially detected it. Now we are going to prove it. Okay, so whenever we are going to prove it, this is already we have seen it, like which is like is equivalent to, is less than or equivalent to L of k. Again, if you have any doubt also, I'm just making changes of this color. Suppose I'm going to add it for this machine, I'm just saying it is L minus processing time. For suppose 2 I'm taking as an example. So if I'm considering this one, the time is equivalent to all the loads for the timing. If I'm not added the job, I'm just removing that job. Now if I'm just drawing a line, I must tell, so definitely this is equivalent to all the loads. Whenever I'm adding it, the load will be different. So this is what we said, and now I'm just changing the color. this is what it said, like it is less than or equivalent to all the machines there. So we have seen like it is equivalent for us. For this case we found equivalent. Sometimes we are getting less than the other loads also. Clear? So whenever we are going for the sum of inequality for this one, so I must tell you, for all the machines L of I minus, for all the machines I have to write it here also, machines we are just multiplying with L of I T of j, which is less than equal to, we are just adding k, which is 1, up to all the machines with the load k. Okay, so next step is that m will be divided there. For all machines we are just adding up to this one, so m is getting multiplied initially. Next we are getting this one. So previously we have said like L of k means the load of that one will be processing time, like sum of all the processing time. So this is as per the lemma one we have proven. So this one is equivalent to the optimal, less than equivalent to the optimal result, or optimal load, or optimal max span you can say. So whenever we say L of I, so this is we recently have proven. Next, definitely the load which is being assigned is less than that. So the example I must tell you, so 3, which is a maximum one, you can say the T of j means the left which we have already left with. So that you can say the job j, which is just we left with 3. 3 is definitely less than, 3 is definitely less than the optimal one, or equivalent to that. Here it is written as equivalent to or less than that. So if you can count all this, so you'll get 2 L star means 2 optimal. So whatever the optimal that you, whatever the approximate value that you are getting is definitely less than equal to Li, definitely less than equal to 2 into L star. Okay, this is what we have proven using greedy approach. The next one, for LPT rule, which is longest processing unit with just longest processing time. So here the time is just, we have taken just an unit for it, might be microsecond, second, anything you just take care of. But LPT basically longest processing time, we are just adding with the just we have sorted all the jobs from in a descending order. Okay, in a descending order, what we did, just initially we have not taken it in a list scheduling. We just did as we have completed earlier, that we have completed this one. But in least process, longest processing time, so we have doing in descending order. It is written in this one descending order. We first initially kept this one, and based on that we are, and we are giving all the processes, like without any fixed order we did in list ordering. But here in longest processing we are keeping first the highest processing unit will be provided to the first processor, which is having a smallest job. Okay, this is how we are doing it. Next, it is also taking the same n log n. Why? Because sorting we are doing. So initially we are getting n log n also. For due to sorting we are getting the time complexity within this also. The time complexity is n log n now. Next observation. This is just the observation whether we are getting the less as compared to the greedy, which is we initially used or not. For that we have to use pigeonhole principle. In the pigeonhole principle, what it says, suppose we are adding one more job to it. So whenever we are adding one more job, we have to sort it. Whenever we have to sort it, definitely we must know. So T1 is already, like we said, we are following this descending order. T2 like this, definitely we will expect the job which is added the last, we have to say it follows this condition. Okay, it follows this condition. Next, whenever we said the list one, if we are picking, so that jobs with m machines, so that at least one machine gets two jobs, means two jobs will be assigned as per the pigeonhole principle. I'm not deciding that one, it is already being decided by the pigeonhole principle. So it says basically whenever we are assigning this m plus one job, means a list job, So that time at least one machine will get two jobs, means to be assigned. So based on the rules, whether it is which type of approximation, if we go for it, so we must tell you. So it is, as we have already proven it, like it is less than L star. This one, as we have already told, two jobs. Based on the two jobs, I must tell you, if we are just running one job there, so we are taking L star. If it is two jobs, so we are just dividing it by two. So whenever we are dividing it, so we are getting it is Li is less than equal to 3 by 2 L star, or sometimes we are writing it 1.5, or sometimes we are writing Li is less than 1.5 L star. Okay, means this represents 1.5 approximation. Approximation. I'm just writing it here. Maybe it is not visible, or Li is less than 1.5 L star. This is what our result said, 1.5 approximation. So which is definitely less than 2 approximation. So LPT gives 1.5 approximation, means the epsilon is 0.5, half of it. Okay, so one is that represents the optimal solutions. What extra that we are getting? 0.5. Instead of getting 6, here we are expecting 4.5 kilometers. The optimal is 3 kilometer. This is optimal. This is our approximation one. So it is 1.5, means just 3 is represented as 1 and 0.5 is 1.5. So total is 4.5 kilometer. Instead of getting 6 kilometer earlier, we are just reducing to this one. So whether it is tight or not, tight in the sense whether this one is fixed or not. How to prove that one? If you just go for it, obviously it is not tight. Why? Because as per the Graham rule again, 1969, it is written there in a content. So LPT rule is providing 3 by 4 approximation, which is nearly around, you can say 3.2 to the bar. Okay, 1.3 bar. Okay, approximation. So this is what we can expect as the value. I'm just writing it here, 1.33 approximation. Okay, this is what we can expect, and essentially yes, this is tightly basically we can expect this one. For an example, they have said there are two types of jobs. We are just keeping with m plus 1, two jobs we are providing with m, two jobs we are assigning again for one machine as m plus 2. Then like this we are just going forward that one, and we'll expect this one. This is not, by the way, in our syllabus. That's why we are not following that one, but at least we shouldn't say 3 by 2 analysis is tight. No, 4 by 3 is also there, which is being taken care of, like the grams. Again, he started with 1969. So I hope this is clear to you how the load balancing is taking places. If any doubt, please comment below. Thank you and have a good day.